Hello and welcome to our lesson on derivatives of exponential functions. So before we get into the exponentials, I just want to do a little recap of the chain rule that we talked about in our previous topic. So the chain rule says that if we are taking the derivative of a composition of functions, so if your function is made up of the composition of two others, then when you take the derivative of that function with respect to x, you're going to take the derivative of the outer function, sort of ignoring the inner function, and then after you take that derivative of the outer function, multiply by the derivative of the inner function. So what we're going to do with the chain rule is exactly what in this lesson is exactly what we did in the previous lesson. We basically use it to generalize our other derivative rules. So this chain rule can be used to generalize our other derivative rules. So we did this in the last lesson. I just didn't say it explicitly, so let me do that here. For instance, if we were to look at the power rule. So the power rule would apply to a power function like y equals x to the third power. We said if we're going to take the derivative of something raised to the nth power, all we have to do is multiply by that exponent, that's why we see this here, and then reduce that exponent by 1, and that's what we see here. So really, simply we would say here, if y equals x cubed, then y prime, or the derivative of y with respect to x, would be 3 times x squared. Okay, so if this was now, instead of just an x being cubed, 5x minus 1 being cubed, this is a composition of the functions, of two functions, so it's a linear function plugged into that cubic. So we would still be taking the derivative of that outer function, right? We would have y prime equal to 3 times, instead of x being cubed, it's 5x minus 1 being cubed. And because that inner function is no longer just an x, the chain rule said, okay, then multiply by the derivative of that inner function, which would be a 5. And it's the same rule, but again, multiplying by the derivative of that inner function. Oops, same rules, which means this should be a 2. So, same rule, okay? If we were to generalize our power rule using the chain rule, if we have x to the nth power, we're going to multiply by x by n and then reduce n by 1. If instead of x, I have anything else, like a 5x minus 1 or whatever it is, as soon as x changes to something else, so let's just call it u to the nth power, we're still going to use our power rule, leaving u alone. So multiply, reduce this by 1, but then again, if this changes from u to anything, or from x to anything else, and again I'm calling it u here, then after we take our derivative, multiply by the derivative of u. So take the derivative of u with respect to x and multiply that. That's going to be your general power rule, but that's the chain rule applied to the power rule, if that makes sense. Okay, so let's look at exponential functions and then generalize them with the chain rule. So an exponential function, if you remember, means a function has a variable exponent. So it's got a variable exponent, which means something like y equals 4 to the x, or y equals 1/2 to the x, or y equals e to the x. Those are all examples of exponential functions. Keep in mind that our base of our exponential function, so like the base of 4, the base of 1/2, the base of e, is somewhat restricted. It can be any real number that is greater than 0, so we're not going to have a base that's less than 0. If we have a negative in there, less than 0 would be negative. That negative is considered a transformation. So our base should be something greater than 0, but it can't be 1, because if we had 1 raised to any power, the result would be a 1. And if all of our results, our outputs, our function values were 1s, we would have something constant or linear and not exponential. Okay, so that's an exponential function, just to make sure we're all on track with what I'm talking about here. We're focusing on, though, finding the derivative of an exponential function. So we could use our limit definition and go through a really nice proof of why this is the case. But at this point, we just need to be able to apply our derivative rules. So if we're taking the derivative of an exponential function, that derivative will be the original function. So we're going to copy it over, and then it's going to be multiplied by, so times, the natural log of the base of that exponential function. So if I am taking the derivative with respect to x of an exponential, so a to the x, 4 to the x, e to the x, 1/2 to the x, whatever it is, it's going to be that original function in the derivative, just copy it over, multiplied by the natural log of our base. And that's it. That's our derivative rule. So rather than, again, using our limit definition and going through the proof, that's it. Now, as soon as x changes to something else, like instead of an x, it's a 3x, or it's an x cubed, or it's a 2x minus 1, we do the same thing. So this is applying the chain rule here to generalize our derivative rule for exponentials. As soon as x is anything else, so as soon as the exponent is anything but just an x, we'll do the same thing, but multiply by the derivative of that change, of that transformation, of that inner function. Okay? So let's try it here. If I was looking for the derivative for y equals 5 to the x, let's say y prime, or the derivative of y with respect to x, would be the natural log of the base, so a natural log of 5 here, multiplied by that same original exponential function. And that's it. So it's the natural log of 5 times 5 to the x. And you can't do anything to simplify that. This natural log of 5 just represents some decimal amount, so we can't do anything to actually multiply or combine it with the base of the exponential on the other side. So that's it. Okay, same thing here. If I wanted to find the derivative, this would be y prime. It's the natural log of my base, and now my base is a fraction, so I'm going to keep it in parentheses there, and that gets multiplied by the original exponential function, so 1/3 to the x power. Lots of parentheses in that one, but that's all. Okay, natural log of the base times the original function itself. Boom. Now, as soon as our exponent is anything else, anything other than just an x, then our chain rule says multiply by the derivative of that inner function. So y prime here would still be the natural log of our base of 4 multiplied by our original exponential function, so 4 to 3x, but because this is no longer just an x, we're going to also multiply by the derivative of that inner function, which is just going to be a 3. And there it is, our derivative. Now I would probably, you can leave it here, this would be totally acceptable as an answer, but I would probably move the constant multiple to the front, but it doesn't matter, so you can write it like this, or you could say y prime is equal to 3 times the natural log of 4 multiplied by 4 to the 3x power. But again, be careful with this. Remember, natural log of 4 just represents some decimal amount. So when you're multiplying by 3, you can't just multiply the 3 in the argument of the log, so we're not going to make that a 12, for instance. If you did want to condense this, you'd have to remember some rules from college algebra. You could bring this 3 up as a power and call this the natural log of 4 cubed, or the natural log of 64, and then multiply this by 4 to the 3x, but I'm not so concerned that you remember those rules, so I'm going to just get rid of that. Okay. But either one of these answers would be fine. I am totally happy with this answer here, but for myself, like to put the constant multiple in the front. So either way, totally fine. Okay. Now, this is not too bad of a rule, but remember, we have other rules that could be combined. So let's take a look at this next example where we have an exponential function, but it is being multiplied by a linear function. So this is really a product of two functions, which means we will apply our product rule. So let's call this first function f, and let's call this exponential function g. So in this case, our derivative is going to be f prime g plus fg prime. So there's our product rule. And now we're going to use our product rule in addition to our exponential rule. So we're going to say y prime in this case will be f prime. So the derivative of our linear function there is just going to be a 1. We're going to multiply that by g as is. So 2 to the x plus 3 power. And then we're going to add on f, which is just x, multiplied by g prime. So now we're going to take the derivative of our exponential. So that's going to be the original, it's going to be the natural log of the base multiplied by the original exponential function. And then because the exponent is not just an x, we should multiply by the derivative of that inner function. So the derivative of x plus 3 would just be a 1. And then we're good. Again, you can leave this as is. I would probably simplify it a little. So 1 times 2 to the x plus 3 would just be 2 to the x plus 3. Plus over here, again, multiplying by 1, not going to change anything. So I would just call this x natural log of, that looked funny, x natural log of 2 times 2 to the x plus 3. So that step in simplifying, I think, makes perfect sense. You might be tempted to take one more step here, and I might as well, although this is not an expectation. Recognize that you have a term here and one term here that have a common factor, so you could also factor out the common 2 to the x plus 3 here. So if you wanted to put this in factored form, you could also say y prime is equal to, if I factored out 2 to the x plus 3 power, we would have left here a 1, and then here we would have our x natural log of 2. So if you factored, because those two terms have that common factor, this would be the factored form of the answer, although that's not a requirement. Again, I'm okay with either one of those answers. Now when you do your homework, I'll try to enter as many possibilities so that you can enter either one and get it correct. If this is on a quiz, I would take either one of these answers, even if it marked you wrong because I didn't input something the way you did, I would still go back and give you the credit. So either one of those would be perfectly fine. All right, so that's how we take the derivative of an exponential function. Now I want to turn your attention to what if the base of our exponential is an e. So if we have a base of e, first of all, do you remember what e is? So let's do a little recap on that. This is Leonard Euler's number e. Hopefully you remember from college algebra that e is an irrational number. Irrational meaning it is a non-repeating, non-terminating decimal, or it cannot be written as a precise fraction. So it's like pi, okay? So pi, we remember pi as 3.14, but it's technically 3.14159 dot dot dot. It goes on forever without any pattern or repetition. So e is similar. It is a very natural base for exponential functions, and it has a lot of ties to compound interest, which, if that sounds familiar, awesome. If not, don't worry about it. Now, we remember pi as 3.14. We need to remember e just as replacing about 2.72. So it's 2.71828. Again, it goes on forever without repeating, without any pattern, but we round it and remember it as approximately 2.72. So if in your head you know that pi is about 3.14, it'd be equally great for you to remember that e is about 2.72. Okay. Now in calculus, we have a more fancy definition for it based on a limit, and I'm going to come back to that at the end of the lesson if you want to hear it. If not, you can just tune me out after I'm done. So for now, what if the base of our exponential function is an e? So let me take your attention here, not here, here for a second. We said if we're finding the derivative of an exponential function, it's the natural log of the base times the original exponential function. Well, let's just apply that rule here. So if I was finding y prime and my base was e, then I would have the natural log of that base e, and then I would multiply by my original exponential function, which would be e to the x. Now again, I don't know how much you remember from college algebra, but the natural log of e has a value, which you could use your calculator for, hoping you don't need it, but if you were to take the natural log of e, the natural log of e is equal to 1. So this really just becomes 1 times e to the x, which makes it e to the x. So when our base is e, our derivative is the same as our original function, which is a little bit mind-blowing. Now a couple side things. Why is the natural log of e equal to 1? So if you remember common logarithms, like if I had the log base, let's say 7 of 49, when we're evaluating a logarithm, we are asking ourselves the power of the base of our logarithm that makes the argument. So in this case, what is the power of 7 that makes 49? Well, that's 2. And so we would say the log base 7 of 49 is 2 because 7 to the second power makes 49. And that is precisely why the natural log of e is equal to 1, because the base of our natural log is e. So this would be asking e to e to what power makes the argument here of e, and e to the first power is going to take it back to itself. So natural log of e is 1, which is why we end up with the original function and the derivative being exactly the same. Okay, so if I want to find the derivative of an exponential function base e, it is itself. Alright, so the derivative of e to the x is e to the x. That was probably the easiest one you can remember if you want to commit that to memory. Now, just like with the other functions, we can, or the other derivative rules, we can generalize as soon as x becomes something else. So instead of an x, it's a 2x. Instead of an x, it's a 3x cubed, or whatever it is. We have to keep our function, right? It's itself, but then multiply by the derivative of that inner function. So we apply our chain rule. As soon as x changes to something else, multiply by the derivative of that something else. Okay? Now, if you're still wondering, how can the derivative of a function be the same as the original function? Like, that's when I first was learning this, was just hard for me to understand. I want to try to show you graphically. Again, this will tie back to one of our previous lessons, so it's always good to connect the dots, right? If I was looking at this function, the graph of e to the x, which looks like a typical exponential function, crossing the y-axis at 1, having a horizontal asymptote here at 0, and growing exponentially or increasing exponentially as we follow it from left to right. If I just read this graph and try to make the graph of its derivative, I would analyze the slopes and graph those slopes as the derivative, because that's what the derivative is, right? It's the slope at each one of these points. So what's happening at the slopes as we go this direction is they're really flat, right? So this entire graph is increasing. Remember, increasing means our slope has to be positive. Get off my highlighter for a second there. So all of my slopes here are going to be positive, which means my entire graph will be above the x-axis, right? Positive, above the x-axis. So I know I'm going to have a graph that's above the x-axis. But what is the actual values of these slopes? So over here, my slope is like pretty horizontal at each one of these points. Is really close to 0. Now, it's not actually 0, but closer and closer to 0. So on this side, we would have graph that is closer and closer to 0, slopes that are closer and closer to 0. Now, it does start to increase as we move along, so the slopes here will increase. Now, what happens when we're looking for the slope, let's say, at 0? So the slope of my tangent line here, well, that's going to be like, go right 1, go up 1. That's about a slope of 1. So at 1, my slope is 1. And what happens is my slope will continue to increase. So let's say I wanted the slope here, for instance. My slope here would be, I don't know, something like go over 1 and go up maybe like 3 or 4. So at 2, my slope is going to be about 3 or 4. Okay, so we're going to be increasing here our slopes and having the exact same behavior that we see on our original function. So e to the x and its derivative are exactly the same behaviors. They're increasing and positive in the exact same places. So seems a little strange, but it can absolutely happen. All right, now let's practice differentiating. So the derivative of e to the x is itself. As soon as x changes to something else, we multiply by the derivative of that something else. So here we would say f prime of x is, again, e to the x would be itself, so this would be itself, e to the 2x, but because that is not just an x, we will multiply by the derivative of that, and so the derivative of 2x would just be 2. So I'm going to make this, again, you can leave this here, but I prefer to put the constant multiple in the front, so 2e to the 2x would be our derivative. Okay? Same thing here. We're going to say y prime is e to the whatever is e to the whatever, so e to the negative 3x squared. Now, because that is not just an x, we're going to multiply by the derivative of that, and so this becomes multiplied by, using our power rule, negative 6x to the first power, and again, this would be totally fine, but I'm going to put that multiple out in front, so I'm going to call this negative 6x times e to the negative 3x squared. That's our derivative. Okay, Let's try another one here. Now we have e to the x in this one, but we have, hopefully you're recognizing, a product with that in another function. So 1 plus 2x is being multiplied by e to the 4x. So I'm going to have to use my product rule here. So I'm going to call this f, I'm going to call this g. And I'm going to say y prime is f prime g plus f g prime. So we are looking at, in this case, f prime, so the derivative of that linear function f is just going to be 2. That's going to be multiplied by g, so g is just e to the 4x, plus we're going to multiply by, or in the next term, we're going to have a product of f, which is just 1 plus 2x, and then multiplied by g prime. So now I take the derivative of my exponential, which is itself, and then because this is not just an x, we multiply by the derivative of 4x, which is just going to be 4. And this would be a perfectly acceptable form of this answer, although I would probably do a couple of things to clean this up. So first, we can say y prime is equal to 2e to the 4x. We can get rid of the parentheses there. Plus, here, if I distribute, this is going to become a 4 plus 8x. So a 4 plus 8x that I can then distribute. Let me move that to a different spot. Boom. We'll call this 4 plus 8x that I can then distribute here to the e to the x. So 4, or e to the 4x multiplied by 4 and then multiplied by 8x gives me two new terms. So I'm going to have 4 times e to the 4x, which is 4e to the 4x, and 8x times e to the 4x, which will be 8x e to the 4x. And then these happen to be like terms, so I would take one more step to combine those like terms. Let me use a different color. So I'm going to combine these. If I have 2 of them there, 4 of them there, that makes 6 of them all together. So I'm going to say y prime is 6e to the 4x plus 8x e to the 4x. And I think this would be probably the preferred form. Again, this would be totally acceptable. This would be acceptable as well. This is probably what I would be looking for on the homework. Although even from here I could argue maybe one additional step, because these two terms have a common factor. This would be the step that I would say is definitely optional. These two terms have in common a 2 and an e to the 4x, so if you wanted to factor that out, then that would leave you a 3 plus 4x, so this would be the factored form of the answer, but that step is totally unnecessary. So I think the preferred forms of the answer would be here or here, but I'm not going to mark you off for any of those if we're taking the quiz. On your homework it gets a little choosier, so if you aren't sure about an answer that you get marked off on, just let me know so I can take a look at it. Alright, let's try this one more here using, again, two rules, because this is a quotient of two functions. I can't divide e to the x by x. So this is a quotient of e to the x and a second function x. So I'm going to call this f, and I'm going to call this g, and I'm going to say g prime of x is going to have to use our quotient rule. So that's going to be f prime g minus f g prime over g squared. So in this case, g prime of x is going to equal f prime, so the derivative of e to the x on the top there would just be e to the x. That's going to be multiplied by g. Well, g is just x. Then we're going to subtract f, which is e to the x, and then multiply by g prime. Well, the derivative of x would just be 1, and then all of that is going to be divided by g squared, so that would just be x squared in the bottom. And again, this would be totally fine, although I'd probably get rid of some of the parentheses here. So I'm going to say g, let me just change colors again. I'm going to say g prime of x is e to the x times x will just be x e to the x, minus e to the x times 1 is just e to the x, and that is being divided by an x squared. And so this would be perfectly acceptable form. So would the previous form, but why use all those parentheses when you don't need them? Or again, if you wanted to factor the numerator, the two terms in the numerator have an e to the x in common. So if you wanted to rewrite the numerator as, how about the pen, as e to the x times x minus 1 divided by x squared, that would be the factored form, but not necessary to do that. Okay? Alright, so one more example where we're doing the same thing, just taking the next step. If I'm asking you to find the derivative, I'm asking you to find the slope of the line that is tangent to a function. But if I ask you to find that derivative at a specific location, then we will have to plug that x value in to find the actual slope at that actual point. Okay, so everything we've done is with derivatives is the slope of a tangent line, but let's figure out what it is at x equals 1 in this case. So a couple ways to look at this. Remember when we have a function multiplied by a constant, the constant multiple rule we talked about in our first day of derivatives is just the derivative multiplied by the constant. So if I'm looking for f prime of x here, it's just going to be 6 times the derivative of e to the x to the third power. So 6 times e to the x to the third power. So it's itself, and then multiplied by the derivative of this thing, which is no longer just an x, right? Multiplied the derivative of that inner function. So the derivative of x cubed is going to be a 3x squared. So we're going to say f prime of x, after we clean it up a little, is 18 x squared times e to the x cubed. That looks funky, but now if I said find the derivative, we're done, because now I'm asking you for the derivative at x equals 1. Then our derivative, our slope, is going to be found by plugging that 1 in. So what is f prime of 1? Well, that's going to be 18 times 1 squared times e to the 1 cubed power. So 18 times 1 squared, that's still 18. 1 cubed is 1, and e to the first is going to be e, so it's going to be 18e for our slope. And then if I asked you to take the next step of writing the equation, then we'd have to use the slope in the point of tangency in our point slope form. But I don't know that's all necessary here. So I'm going to call it done for finding derivatives of exponential functions. So if you're good, this is enough for you to get your homework assignment done. But I want to now just take another minute or 2 or 10, no, I don't know, to explain this a little bit more, and again, make a connection to college algebra. So if you're good, you can turn it off, tune me out, totally fine. But if you like learning, like I do, then let's look at this definition, calculus definition of E. So here, if you remember from college algebra, compound interest. There are 2 formulas for compound interest. There's a compound interest formula for when interest is compounded n times per year. Like annually would be once per year, semi-annually would be twice per year, quarterly would be 4 times per year, and you can just keep changing n. Now if interest is compounded continuously, that just means over and over and over, we have this PERT formula that we use instead. Now that PERT formula has e in it, comes from the interest compounded n times per year formula. So let me show you the connection and how e ends up being the limit of a function. So if we're compounding interest n times per year, let's first just suppose that it's $1 invested for a year at 100%. So that means that p, our principal, would be 1, t, our time, would be 1, and r, our rate, would be 1, so that we don't have to worry about the impact of those variables, because whether you're using this formula or this formula, if your principal, rate, and time are the same, they should not have an effect. So all we're essentially looking at is 1 over 1 over n, or 1 plus 1 over n to the nth power compared to e on this side, because we're going to take out the p, r, and t from the picture, okay? So how do those things relate? Well, if we have a equal to, again, a principal of 1, so $1 invested at a rate of 100%, compounded n times per year for the 1 year, up here would just be an n as well. What's going to happen as n gets larger and larger and larger? So let me take you to the calculator for a second, because I don't actually want to do this calculations. So I'm going to put in a table here, and on this side I'm going to look at what happens as n, which I'm going to call x in this, gets larger and larger and larger. So if I have $1, and then it's 1 plus a rate of 1 divided by n, sorry, I should have had this set up already, to the nth power. So here's the formula, okay? So when n is 1, that means I compound interest one time for the year for that dollar at 100%. My final amount according to this computation here, is going to be $2. Now if I compound interest twice per year, if n becomes 2 semi-annually, then all of a sudden, oops, this is not right. Raised to the x1 power. There we go. If I compound interest twice for the year, then my final amount earned is going to be, or my final balance would be $2.25. So I have more money if I compound interest more times. If I compound interest 4 times for the year, then I end up with $2.44 at the end of the year. If it's, let's say, 6 times for the year, it's $2.52. And the more times I compound interest, the more interest I'm going to earn on interest, and that's why this is happening. So let's say it's, I don't know, 12 months. Every month we compound interest, or every week we compound interest, or every day we compound interest, or maybe I compound interest 1,000 times, or maybe 10,000 times, or 100,000 times. What you're going to see is the outputs in our table are getting closer and closer and closer to about 2.72, the value of E. And so this right here is what we said for the definition of E. As n is approaching infinity, as n gets larger and larger and larger, we can see that decimal gets closer and closer and closer to E. So we say in calculus that E is going to be exactly, so not approximately, but exactly, the limit as n approaches infinity, gets larger and larger and larger, of 1 plus 1 over n to the nth power. So this comes directly from compound interest, and that's what this formula comes from here. So the PERT formula is E as our base, but E is, as we compound interest an infinite number of times, we see the result here of E. So I don't know if that came out exactly how I wanted it to, but hopefully you see some connections between what you did in college algebra and these formulas, and now we have a nice precise definition for E instead of just saying, oh, it's Leonard Euler's number and it's about 2.72. So it's the limit as n approaches infinity of 1 plus 1 over n to the nth power, but that is compounding interest n number of times. As n gets bigger and bigger and bigger, we have an output that is closer and closer and closer to our value of E. Okay, so if you like learning, hopefully that was cool and you made some connections to college algebra. But like I said, what we did here at the end of this was good for you to get your homework assignment done. In either case, if you have any questions, please reach out. Until next time, take care.